Welcome you in the lecture series of random processes, detection and estimation. It is 20th lecture of this series. Till now we have discussed about the detection of a signal in presence of noise by detecting the change in the mean of the test statistic because we have assumed that the signal is deterministic. In some cases, the signal is modeled as a random process. In this lecture, we will discuss about the detection of random signal. Now, the outline of this lecture are energy-detector and estimator-correlator. In the objective of this lecture, you will able to explain how can you detect the signal when it has random nature. We can detect the deterministic signal by detecting the change in the mean of the test statistic. In some applications like speech processing, signal is a more appropriate model as a random process because the waveform of a given sound depends on the identity of the speaker, means the context in which the sound is spoken or the health of the speaker, etc. So it is not appropriate to assume that the signal is known. A better approach is to assume that the signal is a random approach with known covariance structure. When the signals are modeled as random process with known covariance structure, then the detector takes the form of estimator-correlator to copy which is the random nature of the signal to be detected. So, what is energy-detector? Assume that the signal to be detected is a zero mean, wide sense stationary Gaussian random process with known covariance. The noise is assumed to be white Gaussian noise. First we drive NP detector for detecting the signal. Later it is generalized for the case when the signal is modeled as the Gaussian random process with known arbitrary covariance matrix. So let us take the case first. Detection of the random signal when the diagonal covariance matrix is given. Means in the covariance matrix we have non-zero on the diagonal, and other than diagonal we are having 0 in the covariance matrix. Let two hypotheses H0. The hypothesis H0 corresponds to Xn is equal to omega n, means under hypothesis H0 there is no signal, only noise is present, and under hypothesis H1 Xn is equal to Sn plus omega n, where the signal is a signal in presence of noise, and small n is equal to 0, 1, 2, n minus 1. Where Sn is 0 mean wide sense stationary Gaussian random process with variance sigma s square, and omega n is the white Gaussian noise with variance sigma square, and independent of the signal. Now, two hypotheses can also be written as under hypothesis H0, matrix X having the normal distribution with mean 0 vector and covariance sigma square I, and under hypothesis H1 the X having the normal distribution with 0 matrix and covariance matrix is the sigma s square plus sigma square into identity matrix. Now NP detector decide H1 or H0 if the likelihood ratio, means the PDF under hypothesis H1 divided by PDF under hypothesis H0 greater than less than threshold value gamma, and here the PDF under hypothesis H1 it is equal to 1 by 2 pi to the power n by 2 into 1 by sigma s square plus sigma square to the power n by 2 into a to the power 1 by 2 into sigma s square plus sigma square summation n0 to n minus 1 x square n, and PDF under hypothesis H0 it is 1 by 2 pi to the power n by 2 into 1 by sigma to the power n and into a to the power minus 1 by 2 sigma square summation n0 to n minus 1 x square n. So the likelihood ratio test, it will be Lx is equal to 1 by 2 pi to the power n by 2 into 1 by sigma s square plus sigma square is to the power n by 2 into e is to the power minus 1 by 2 sigma s square plus sigma square summation n0 to n minus 1 x square n, and the PDF under hypothesis h naught, it is 1 by 2 pi to the power n by 2 into 1 by sigma is to the power n into e is to the power minus 1 by 2 sigma square summation n0 to n minus 1 x square n, and this is greater than less than some threshold value gamma. So I can also write it as the likelihood ratio, it is Lx is equal to sigma square upon sigma s square plus sigma square is to the power n by 2 into e is to the power minus 1 by 2 sigma s square plus sigma square plus 1 by 2 sigma square summation n0 to n minus 1 x square n, and it is greater than less than threshold value gamma. Now taking the natural log likelihood ratio test LLRT, it will be n by 2 log e sigma square by sigma s square plus sigma square minus 1 by 2 into 1 by sigma s square plus sigma square plus 1 by sigma square summation n0 to n minus 1 x square n. It is greater than less than log e gamma, or I can write this expression as 1 by 2 log e sigma square sigma s square plus sigma square plus 1 by 2 sigma s square by sigma square into sigma s square plus sigma square into n is to the power 0 to n minus 1 x square n. This is greater than less than log e gamma, or I can write this expression as 1 by 2 sigma s square divided by sigma square into sigma s square plus sigma square into summation n0 to n minus 1 x square n. This will be greater than less than log e gamma minus n by 2 log e sigma square by sigma s square plus sigma square. So I can also write this as if I put this expression in the right side, then it will be sigma n0 to n minus 1 x square n greater than less than 2 sigma square sigma s square plus sigma square by sigma s square minus n sigma square into sigma s square plus sigma square by sigma s square log e sigma square by sigma s square plus sigma square, and this is the new threshold value gamma dash. Here this is log e gamma minus, this is the new threshold value gamma dash. Now we decide h1 or h0 test statistic tx means h n0 to summation n0 to n minus 1 x square n greater than less than threshold value gamma dash, and this is the energy of the signal. So Energy-detector computes the energy in the received data and compare it with the threshold, so it is known as Energy-detector. If the signal is present, the energy of the received data increased. Equivalently, the test statistic, it will be t dash x will be 1 by n summation n0 to n minus 1 x square n is an estimator of variance, and compared to the threshold, variance under h0 is sigma square and under h1 it is sigma s square plus sigma square. Here the test statistic is the sum of the square of n independent identically distributed Gaussian random variables. So the detector performance under both hypotheses, it will be under hypothesis h0 xn square will be tx by sigma square, and under hypothesis h1 xn square, it will be tx by sigma square plus s square. And here q function of x, where x c v square, it will be equal to integration x from x to infinity pt dt, for x v square is a random variable. So the probability of false alarm, it will be the probability of test statistic greater than gamma dash under hypothesis h naught. So it will be the probability of test statistic tx by sigma square and greater than gamma dash by sigma square under hypothesis h naught. So it will be q function gamma dash by sigma square, and the probability of detection, probability of test statistic greater than gamma dash under hypothesis h1, it will be q function gamma dash by sigma square, sigma s square plus sigma square, or it can be the q function gamma dash by sigma square divided by sigma s by sigma whole square plus 1. So as so you can also write it as q function of gamma double dash sigma s by sigma whole square plus 1. The gamma double dash is gamma dash divided by sigma square, and you can see as sigma s square by sigma square increases, the probability of detection is also increased. The energy detector forms the most widely used receiver in communication system. In practical, for the asynchronous communication, this is most widely used, and the detection performance of the energy detector is you can see the detection performance, the probability of detection versus SNR, you can find with PDF with the probability of false alarm PF is equal to 10 to the power minus 5. This will be the curve for the PD, and if I am going to increase the probability of false alarm, then the curve will be like this. So from here you can see the probability of detection increase with increasing the SNR, and also the probability of detection also increase with increasing the probability of false alarm. Now consider another case, second, detection of a random signal with arbitrary covariance matrix. This is known as the estimator-correlator detector. In the previous case, diagonal covariance matrix was given, where in the diagonals there are non-zero elements, and other than the zero elements were there. Now in this case, detection of random signal with arbitrary covariance matrix. Let two hypotheses h naught corresponds to xn is equal to omega n, means under hypothesis h naught there is no signal, only noise is present, and under hypothesis h1 xn will be Sn plus omega n, where small n is equal to n 0, 1 to n minus 1. Here Sn is 0 mean Gaussian random process with covariance matrix CS. Now this time you have given the covariance matrix, and in the previous case you have given the covariance of the signal was sigma s square. Now the covariance matrix is sigma CS, and omega n is the white Gaussian noise with zero mean variance sigma square. So for this model, the two hypotheses will be under hypothesis h naught. X will be the normal random variable with mean 0 and variance sigma square I, and under hypothesis h1 we will have the normal random variable with mean 0 vector, and the covariance matrix of this it will be C. So now the NP detector, we apply the NP detector, and this will decide h1 or h naught. If the likelihood ratio Lx, it is 1 by 2 pi to the power n by 2 into 1 by under root determinant of Cs plus sigma square I into e to the power minus 1 by 2 x transpose into Cs plus sigma square I and inverse of this matrix Cs plus sigma square I into X divided by the PDF under hypothesis H naught. It will be 1 by 2 pi is to the power n by 2 into 1 by sigma is to the power n into e is to the power minus 1 by 2 sigma square x transpose x, and it will be greater than less than threshold value gamma. Taking natural log both sides, you will get log likelihood ratio. It is 1 by 2 x transpose into inverse of the matrix Cs plus sigma square I minus 1 by sigma square I into x greater than less than threshold value gamma dash, or the test statistic Tx, it will be sigma square x transpose into 1 by sigma square I minus Cs plus sigma square I into x greater than less than 2 gamma dash sigma square. And now using the matrix inversion lemma, that is A plus B C D means inverse of the matrix A plus B C D, it will be equal to A inverse minus A inverse B, and the inverse of the matrix A D inverse B plus C inverse into D A inverse. So let here A is equal to sigma square I, B and D is equal to identity matrix, and C is equal to CS. Then sigma square I plus CS inverse means the inverse of the matrix sigma square I plus CS. It will be equal to 1 by sigma square I minus 1 by sigma is to the power 4 into the inverse of the matrix 1 by sigma square I plus CS inverse. So the test statistic, it will be here Tx is equal to x transpose into 1 by sigma square and the inverse of the matrix 1 by sigma square I plus Cs inverse into T into x. Now consider it is S cap. So the test statistic, it will be x transpose S cap, and S cap is equal to 1 by sigma square and inverse of the matrix 1 by sigma square I plus C inverse into x, or I can write it as 1 by sigma square CS plus sigma square I CS inverse, and take the inverse of this matrix 1 by sigma square CS plus sigma square I CS inverse and x, or you can write it as CS into inverse of the matrix CS plus sigma square I into x. So we decide H1 or H0 if the test statistic is equal to T x transpose S cap greater than less than gamma dash threshold value, so we decide H1 or H0 if the test statistic means x transpose S cap greater than less than threshold value gamma double dash, or you can write it as summation n0 to n minus 1 xn S cap n is equal to x transpose S cap greater than less than threshold value gamma double dash, where S cap is the CS into inverse of the matrix CS plus sigma square I into x. Here the NP detector correlates the received data with an estimate of the signal, that is S cap, and it is known as estimator-correlator detector, and S cap is actually Wiener filter estimator of the signal. So in the block diagram you can see because S cap is the it is CS plus sigma square I inverse x. So, and this is the estimate of the signal. So first of all you have taken the observed data, and from this passing through the Wiener filter you will have the S cap, that is equal to CS inverse of the matrix Cs plus sigma square I x. So you will get S cap n, and after combining these two, S cap n and xn, taking the summation over 0 to n minus 1, you will get the test statistic, and this will compare with the threshold value. If the value of the test statistic is exceed than the threshold value, then you will decide the hypothesis H1 is true. Otherwise, hypothesis H0 will be true. Now, if the signal is white, then Cs is equal to sigma S square I, and the signal estimator, it will be sigma cap is equal to sigma S square I, and sigma into sigma S square I plus sigma square I into x. And from here you can have S cap is equal to sigma S square divided by sigma S square plus sigma square into x, or you can say S cap n, it is equal to sigma S square by sigma S square plus sigma square into xn. This is the scalar factor. This is a zero memory filter that weights the received data by the fixed scalar factor sigma S square by sigma S square plus sigma square. And here, if sigma S square very greater than sigma square, the weights are approximately 1. And when sigma S square very less than sigma square, then they are near to 0. In this case, the detector simplifies the known scalar factor into the threshold. So we decide H1 or H0 if the test statistic means summation n 0 to n minus 1 xn S cap n is equal to sigma S square by sigma S square plus sigma square summation n 0 to n minus 1 x square and greater than less than threshold value gamma dash. Here from the previous slide, you know S cap n, it is sigma S square by sigma S square plus sigma square into x. So that's why we have written this is in the form of sigma S square by sigma square plus sigma square summation n 0 to n minus 1 x square n. So you can write here as summation n 0 to n minus 1 x square n greater than less than gamma double dash into sigma S square plus sigma square by sigma S square. The estimator-correlator can be generalized when the observation noise omega n is Gaussian but not white. So far in this lecture, we have discussed about the energy detector and estimator-correlator detector. This was the 20th lecture of the lecture series of random processes detection and estimation. In the next lecture, we will discuss about Bayesian linear model and generalized Gaussian detector. Till then, thanks for listening this lecture. Thank you.